Okay, now talking about the Bohr-Rutherford notes. Okay? All right, so we talked about on Tuesday how when electrons are added to atoms, they can't just go anywhere, right? There is a pattern. There are certain laws of nature that determine where the electrons fall, correct? And the different shells, etc. Okay? How many shells are there for all the elements in row 1? Class? Yikes. How many shells are there for all the elements in row 1? One. There we go. Just one shell. How many shells are there for all the elements in row 2?
2.
How many shells in row 3?
3.
How many shells in row 4?
4.
Good. Question. Why do we stop at calcium? Why do we stop at number 20? Raise your hand. Sophie, why? Very good. The rules start to change. Up until this point, every time you add electrons, they go in the outermost shell. Do you have something in your lap? Stand up. Bring it to me. No, to me. Okay. So every time you add electrons, they go in the outermost shell. After this, okay, they start to go into more like the third shell, right? Okay, it goes on and on and on and on. Pattern changes. It's not quite as consistent. But what I want to talk about here is something called valence electrons. Okay, new term for us. So at the bottom of the paper, I want you to write valence electrons. And then we're going to write the definition. The valence electron is the number of electrons in the outer shell only. It does not include the full shells. Okay, copy it down, then I'll explain what that means. The number of electrons in the outer shell only. This does not include the full shells. I'm going to explain it. Just write it down. Does not include any full shells. Okay? Hold on. All right, so let's look at hydrogen first. Okay? How many valence electrons does hydrogen have? How many electrons does it have in the outermost shell?
1.
1. Okay? Look at helium. How many electrons does it have in the outermost shell, not including the full shell? 0. Very good. Okay? Because the first shell is full, it can hold a maximum of how many electrons? 2. Because this shell is full, and it has no other shells, no other outer electrons, it has 0 valence electrons. You see what I'm saying? Valence electrons are a special kind of electron. Yes, there are 2 electrons total in this atom, but there are 0 valence electrons because this whole outer shell is full. Okay, so take your pencil or pen, whatever you're using. I want you to trace that outer shell. We're gonna use that as our key to show us that that shell is full. Nicholas, you with me? Okay. Just on helium. For right now. Quickly. Just do what I do and it will make sense. Yes.
What was in the parentheses?
Not include full shells. Okay? All right. Now, go to lithium. Lithium has 2 shells, correct? How many shells are in the first, or how many electrons are in the first shell? 2. Does that fill it up? Yes, it does. So trace the first one. No. I'm only using a different color to help you see the difference. Okay? So now, how many valence electrons does lithium have? 1. Very good. It has 1 electron in the outer shell, in the shell it's not full. So below that, I want you to put V1. We'll go ahead and write that for hydrogen too. V1. Not yet. I think you probably got it, but hold on. Okay, let's go to beryllium. We just started class, hon. Are you okay? Okay, go ahead. All right, for beryllium, okay, the first shell is full. It has 2 electrons. It's totally filled up. So trace that. So that means that beryllium has how many valence electrons, class?
0. Oh, sorry, 2.
2. Very good. 2 in the outermost shell. So we're going to put V2. Okay. Now let's go to boron. Again, boron has a full first shell. And how many valence electrons? 3. Let's go to carbon. First shell is full, so we're going to trace that. Raise your hand. Someone tell me how many valence electrons then are there? Ashley? 4. Very good, because the outer shell has 4 and the outer shell is not full. So it has 4 valence electrons. Okay, now finish up the whole rest of the row. Nitrogen has a full first shell with 5 valence electrons. Oxygen has a full first shell with how many valence, class? 6. Fluorine has a full first shell with how many valence? 7. Good. And then neon, here's where things get funky. Neon has a full first shell and a full second shell. It's got 2 in the first and 8 in the second. So we're going to trace both shells. So how many valence electrons does helium have, or neon have? 0. Same thing for helium. We can go back and write that as well. Okay, go to the next row. Question?
I get that because it has 0, it's a full shell on each. It has a max number of electrons on each shell.
Mm-hmm.
But why would we not include the second shell and being the shell that we found?
I'm not sure what you're asking. Why do we not include these in the count of valence electrons?
No, why? Like the second one's full.
Uh-huh.
But why wouldn't we count that one because it's the outermost shell?
Because valence electrons because the term means the number of electrons in the outer shell if that shell is not full. If that shell is full, they don't count as valence electrons. Yes.
So that's why in parentheses it says not included in the shell.
Correct.
Oh, that's not.
Okay. Now let's go down to sodium. Okay. Sodium has a full first shell and a full second shell. But now with the third shell, how many valence electrons does it have? Say it out loud.
1.
1. Very good. Magnesium has a full first shell and a full second shell. And how many in the third shell? 2. Is that third shell full? No. So those 2 electrons are considered valence electrons. Ethan? Okay. All right, aluminum has a full first shell, a full second shell, and then how many valence? 3. Do you see a pattern? Yes. All right, pause for a second. Look up here. Hold on, Bella. I'll help you, okay? Notice, all the elements in group 1 have 1 valence electron. All of them. 1 valence electron. 1 valence electron. 1 valence electron. 1 valence electron. All the elements in group 2 have 2 valence electrons. Okay? Now, keep in mind that this group is not actually group 3. It's actually group 13. Okay, this is why. If you look at the table, here's group 1, group 2. We kind of have to skip all these transition elements because they start changing the rules, right? Okay, here is where we pick up, which is group 13. Okay, so group 13, all these elements have 3 valence electrons. Group 14, they all have 4. Group 15, they all have 5. Group 16, they all have 6, and all the way on through. Yes.
So with the 2 bottom ones.
Mm-hmm.
So when it has for ones with 4 shells.
Yep.
The maximum of the 4th shell isn't 2.
Correct. After calcium, so like scantium, which is number 21. Okay. After that, at scantium, instead of adding the next electron in that outer shell, the laws of nature sometimes break the rules and it gets added to the 3rd shell instead. That's why we stop here, because after that the pattern stops. Okay. All right, so let me go back and trace all the full shells real quick. Yep. Ethan?
So does that mean O the next one has no valence electron?
Correct. And then argon, all 3 of them will be full. Yes. Correct, because all the shells are full. Okay? Now, these valence electrons are important for one reason. These are what determine whether or not an atom can bond. Okay? Here's the thing. Atoms are, think of them as like almost unhappy if their outer shell isn't full. Okay? An atom without a full outer shell absolutely has no chill. Okay? Atoms have this natural desire in nature to fill the outer shell. If by themselves they are not full, that's when they bond with other atoms. And they end up sharing or donating electrons and kind of working things out to where they have a full outer shell. Okay? Of the entire table, the only elements that you can find in nature just by themselves is group 18, the noble gases. They're the only ones that exist without bonding to something else. Why? Well, because every single atom in that group has a full outer shell. It has no need to bond with anything else. Does that make sense? The whole rest of the table, everything except for this column. Let me zoom out. Everything except for this group out here, all of these will exist in nature as molecules or compounds of some sort because none of these have full outer shells. Okay? Therefore, they're very reactive and they have to bond with something else. Does that make sense? Okay. So that's where the bonding comes in. And that's where notes number 5 go. So turn to notes number 5 and we'll start filling those in for today. What? All right. Ethan H.
So, with the electrons and asteroids, how many valence electrons do they have?
I don't know because they're in that group that has kind of a different pattern. I could find out in my book, but off the top of my head, I don't know. I'm not sure why everything is taking so long to read. Okay, here we go. Molecules and compounds. Okay, so you should be open to notes number 5. Most of this is going to be review from the vocab. Okay? But I have a few other things I want to show you, and I think it will help make things a little more clear. Molecules. Like we just talked about, some elements can exist as a single atom of that element. Okay? Helium is an example. Helium is one of those atoms that because all of its shells are full, it can exist as just one atom of helium. It doesn't have to bond with anything else. Other elements, however, do not exist as single atoms, but instead they exist as molecules. Every other element besides the noble gases, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all of these are examples of elements that exist in nature as molecules because that outer shell is not full. Yes.
Okay, so I thought when it said they can't exist on their own, I thought that was meaning that you can never find those elements as a pure substance. You have to find them mixed with another element.
No, opposite. They are the ones that you can find. It's just one single atom of that element.
No, I'm meaning the ones that don't have electrons.
Correct. Every single one of them usually. Now they could bond with themselves and still be a pure element, like we were talking about, but they can't exist as just one atom of that element. Bella? No idea. Oh, here? You mean the different elements? Technically, they should be capital, I think. I actually don't know. Good question. Either way, I'm not worried about it. Landon?
Other than oxygen, out of hydrogen, nitrogen, fluorine, bromine, iodine, are there any other
Diatomic molecules? Those are not diatomic molecules. Oxygen is, yes. There are some more that we'll look at here in just a minute. Okay? Caleb?
Oh, yeah. Okay. So when I first studying the
Mm-hmm.
I got really confused on
Yeah. It makes more sense now. Good. Glad. Yeah. right, molecules. A group of the same kinds of atoms or different kinds of atoms can combine. When two or more atoms combine, they form molecules. That's the very definition for a molecule. Two or more atoms that have bonded together. So, molecules are just groups of atoms that have bonded together. Okay? So, for example, I have my little model pieces or whatever up here. Okay? Each little ball represents a different kind of atom. Each color is a different kind. Okay? So, if I had two of these, it's still two atoms, but they're the same kind. Make sense? Okay? These two are two atoms, but different kinds. Make sense? Okay. So, anytime you have two or more atoms that bond together, that's a molecule. Whether they're different or whether they're the same, still a molecule. Does that make sense? If you have three atoms come together, 1, 2, 3, that's still a molecule. You see what I'm saying? Okay. Any of that would be a molecule. The simplest molecules are those that are formed of only two atoms. Only two, no more than two. That is the simplest kind of molecule. Okay? It's called a diatomic molecule. Okay? Di, like we discussed, is another sort of kind of root for the number 2. So literally it means a 2-atom molecule. Okay? For my little models up here, anytime there's a little white stick between the balls, that represents a bond. Okay? So, this right here would be a diatomic molecule. See? This right here, not a diatomic molecule because there are 1, 2, 3. Okay? What else do I have in here? This does not like to stay together, but this right here is also not diatomic, right?
No.
1, 2, and 3. Make sense? Okay, Anna? Oh, just cross it out. Alt. Landon? Mm-hmm. It's not actually a thing, but I have to have some way to stick them together and take them apart. So that in my models, the stick just represents the bond. There's not actually a white stick in between the atoms when they bond. There's nothing between them when they bond. Correct. Yes. Yes.
So I have two things. One, I didn't get molecules or groups of atoms that are bonded together.
Bonded. And
also, is that an atom or a model of an atom right up there?
yes, that big one up there on the wall, that is a glucose molecule made of like 26 atoms or something like that. Okay, quite a few. All right. Actually, I guess this is 24. So. Okay, if the individual atoms are different, then you also could call it a compound. Definition for compound is the exact same as we have in our notes. A compound is a pure substance made of two or more different elements that have a fixed ratio. Okay? Two examples could be CO2, carbon dioxide, which is the model shown right here, and NaCl, which stands for sodium chloride. Okay? So, let's go back to once you finish that, let's go back to my little models here for a second. I know I'm very much in the way. No, this one, the hole is too small. I don't know. Okay, So let's practice. Is this a molecule? It's okay. It only has two. Forget the two things. It's like they're just bonded together. Is it a molecule? Yes. Two atoms bonded together. Is it a diatomic molecule?
Yes.
Is it a compound? Good. No, it's not a compound because they're the exact same. Is this a molecule?
Yes.
Is it a diatomic molecule?
No.
Is it a compound?
Yes.
Good, because there's one kind of atom here, one kind of atom here. Is this a molecule?
Yes.
Is it diatomic?
Yes.
Is it a compound?
Yes.
Good job. Is this a molecule?
Yes.
Yes, it is. Is it a diatomic molecule?
No.
Is it a compound?
Yes.
Very good. See the difference? Okay. Yes. All right. So, here's some other examples of compounds and molecules. Hydrogen gas is just H2. Okay? Two hydrogen atoms that have bonded together. Oxygen gas. This is really more what it looks like, Landon. Okay? They really come together and they actually end up sharing these electrons here. Yeah. So two oxygen atoms bonded together. Okay? Carbon dioxide. One carbon, two oxygen. Nitrogen gas. N2. 1, 2 nitrogen atoms. Water. H2O. 1 O, 2 H. Okay? Salt. Sodium chloride. Sodium chlorine. Okay? More examples. Methane gas is CH4. 1 carbon, 4 hydrogen. Hydrogen peroxide. H2O2. 2 oxygen, 2 hydrogen. Laughing gas. N2O. 2 nitrogen, 1 oxygen. It's like what they give you at the dentist's office to get you to relax. It's called laughing gas. That's not a technical name for it, but because it makes people kind of like loopy almost. You see those videos of people that have the wisdom teeth sticking out? Laughing gas is part of what makes them so loopy. Sometimes. There's other ones too, but laughing gas is a common one. And then quartz. SiO2. Silicon, 2 oxygen. Okay? Then we have the SiO2. No, capital S, lowercase I, capital O. Okay? Then here's the big dog, glucose. Okay? This is C6H12O6, like what we talked about before. Okay? I'll show you. 6 carbons, C6. 1, 2, 3, 4, 5, 6. H12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? O6. 6 oxygen. 1, 2, 3, 4, 5, 6. Okay? 24 atoms altogether. Now, here's what's interesting. The properties of the compound are different than the properties of the elements that make up the compound. Let's take water, for example. Water, we know the formula is H2O. I know that too. H2O. Hydrogen by itself is a gas. Oxygen by itself is a gas. But when you have just the right amount, 2 hydrogen molecules and 1 oxygen molecule, you can get a liquid. A very important liquid, water. Okay? Another example. Another example is kind of fun. Is table salt. Okay? Table salt is made from sodium and chlorine. Now, sodium by itself is a soft, extremely malleable metal that reacts explosively with water. Remember the video of the sodium in the pond? That's sodium. by itself is a poisonous, highly irritating greenish yellow gas, but it's actually used for like tear gas or mustard gas, like chemical warfare. Okay, but when you get one atom of this and one atom of this to bond together, you get salt.
Yellow gas.
You're not eating poisonous yellow gas.
I mean, you're pretty much eating a yellow.
You're not eating metal either. You are eating salt, which is totally, totally different than this and this.
But they bond, so that means the yellow
I know.
gas stuff is. Wait,
I know.
You're pretty much eating yellow gas stuff in.
Okay?
I
And not only that, are we done? Can I finish? Oh, thank you. Not only that, but salt is necessary. We have to have some salt in our bodies. Okay? But oddly enough, it's made out of one atom of a poisonous gas and one atom of a metal. But somehow, thanks to chemistry, the amazing way that God designed it, this is created from these two things. Or from the amazing thing of science. Crazy. Patty?
If chlorine is poisonous and highly irritating, then why is the water in food?
Good question. The chlorine in your pool is not pure chlorine. It's actually a chlorine compound. Good question. Bella? Okay. Let me stop this recording first.